Wow, hope your interview's going well, Pooja, and greetings to you, Rahi. We're doing lots of fun separable differential equations. I'm sure you wish you were here with us. So we're going to have initial conditions. That's the only little new twist here. Thankfully, you know what? You did this last year in BC Calculus. That really was a topic that was covered in that curriculum. You saw it on your AP exam with the initial conditions as well. By the way, tomorrow, brand new material that was not in the calc curriculum. But hey, let's see if we could do some separating of variables. And tell you what, I'm going to try to do this kind of quickly. I'm going to do a little bit of cleaning up. How about we divide both sides by the cosine of x and also multiply both sides by dx. Simultaneously, I'm going to divide right over here, and I'm wondering, with this e to the 2y minus y, wow, we're going to have an issue with that. You can see in just a moment. I think you can begin to see the intervals taking shape even as you're setting them up. But just moving all our terms with y's on the left, moving everything with an x to the right. Hey, when I see the sine of 2x, I immediately think of what?
2 sine x cosine x.
Yeah, 2 sine x cosine x. And some nice things are going to happen. If we can cancel, we certainly should take advantage of it. And how about we do a little I heart math with this right-hand side. And I'm going to clean it up. E to the 2y over e to the y. Would we agree that's just e to the y? And now, shock of all shocks, this is the thing that we maybe don't like to see as much. You're like, wow, that's y all over e to the y, but how about we bring e to the negative y up? Integrating won't be that big of a deal, especially on the right side, but on the left side, maybe a momentary inconvenience. You probably won't have an issue with e to the y, definitely should not. But it's this e to the negative y that's a problem. That's a little bit of a concern. How do you think we've been doing this in the past, integrating something with a y, e to the negative y? Integration by parts is absolutely correct. You remember tic-tac-toe, don't you? Tabular integration by parts. Hey, and tell you what, let's just keep the negative out in front there. Let's see, the derivative of y with respect to y is 1, and then a 0. Oh, be careful, we're going to have to reverse the chain rule. What's the antiderivative of e to the opposite y? Yeah, negative e to the opposite y. Do it one more time, and we get e to the opposite y. And we'll have here and here, so here's our plus, here's our minus. So we'd have a y times e, negative e to the negative y. That would look something like this. Bring the negative out in front. Then bring this negative out in front as well, 1 times that. But you know what? We actually have this negative that's going to be applied to all of that anyway. So we're going to have to change all those signs. I hope it's not too much of a stretch if I just say change the signs here. That we would have this on the left-hand side. Are we okay with that? Yeah, because our integration by parts, we did that off to the side, but you realize a negative would get distributed to our answer. And hey, that's all well and good. How about the antiderivative of 2 sine of x? That just becomes, what's that? Negative 2 cosine of x, and then what? Plus a constant. But they're telling us rather nicely that y of 0 equals 0. So guess what? We've got the point 0, 0. And our ultimate goal is to find that little constant. So we've got e to the 0 plus 0 e to the 0 plus e to the opposite of 0 is 0. And over here, we all know what the cosine of 0 is. Cosine of 0 is 1. So really, this becomes negative 2 plus c. This wipes out. 0 times e to the 0 is nothing but 0. But e to the 0s are really 1s, and 1 plus 1 is 2. So c would equal 4. How would we write our answer? And of course, we would write our answer implicitly in this regard. Maybe the unfriendly looking particular solution, not so bad really. That seems to be all right. You okay with that? Okay, so no big news there. Run-of-the-mill problems where you plug in your initial conditions, find your C, you're good to go. Uh-oh. What about on the back? Here's something that's a little bit more thought-provoking. Look at this. It says, you must be careful since the variable divisors could be 0, you could lose a solution. Oh my goodness. Lose a solution? This doesn't seem to be anything that looks menacing. I hope none of us would think that. Tell you what, how about we just real quickly do a little separating of variables. Divide both sides by y squared minus 4. Multiply by the dx simultaneously. And this is screening out BC calculus back in our good old days. So guess what we'd do back then? We would very quickly do partial fractions. Now, by the way, y squared minus 4 is going to factor into y plus 2, y minus 2. And we could very quickly break that apart. Hopefully you remember partial fractions. And we'd have something that looks like so. We could multiply through by our LCD. I hope you guys remember that. Is this ringing a bell? Right, look at all this. And then we would choose some familiar forms of y to help us out. Maybe let y equal, what do you think? A 2, and that would allow us to go to 1 equals 4b, or b is equal to 1/4. Hey, that's not so bad. And what else could we let y equal? Negative 2. And then if y is equal to negative 2, the expression with the b cancels out, leading us to 1 equals negative 4a, leading us to a equals negative 1/4. So what are we really getting at? This partial fraction would become, and as we'd be integrating this, a all over y plus 2. Well, that's negative 1/4 times 1 over y plus 2. We could separate it in that way. Plus, how about our b? Well, we've got 1/4 for that. I can bring it as a coefficient. Here's our y minus 2, and here's our dy. And the right side's the nice, simple, direct one. That's just the integral of dx. And help me, guys. Hopefully we remember how to take the antiderivative of 1 over y plus 2. What's that? Absolutely. The natural log of y plus 2. Here we have plus 1/4, the natural log of the absolute value of y minus 2. How about the right side? X plus some little pesky constant, right? Okay. So usually kids are looking at this and they're saying, wait a minute. You brought up in the beginning that there was the danger of losing a solution. What on earth are you talking about? Well, tell you what, we could very quickly multiply everything through by 4, perhaps. And if we did that, we would have, and how about I reorder, how about I put this natural log of y minus 2 out in front, and then say minus the natural log of y plus 2. Now, if I multiplied through by 4, of course, we'd even have this 4c. And, wow, tell you what, the 4c, if we think about it, isn't 4c another constant in and of itself? I mean, if you think about it that way, we could certainly get to that. But I'll get to that in just a moment, guys. Look, the left side, the reason why I did all that, would you agree that we could combine into this form? And usually kids are like, well, sure, you can do that. You want to leave that 4c there, you could, and that would be just fine. There's nothing wrong with that. Of course, you want to change it to another constant, equally good. Well, hopefully you can see that we're going to exponentiate both sides. We're going to exponentiate both sides. We're going to say, or as some teachers say, make your log circle. And we'd have absolute value of y minus 2 over y plus 2. And this becomes e to the 4x. If you want to call it a second constant, you may. That would be fine. You know, I brought that up before. And then, of course, we could even pull that. Well, tell you what, how about I just write it as 4c and make it a second constant when we pull that out in front. Remember, we have x to the a times x to the b equals x to the a plus b. We could go from the right side to the left side. In other words, we could say pull out e to the 4c times e to the 4x. And my goodness, as we just continue to work this out, we could just call that an arbitrary constant now. Call that your c sub 2 if you'd like. Well, and by the way, tell you what, how about at the same time, trying to kill two birds with one stone, how about we take our absolute value and say, of course, that could be a plus or minus. But guys, look, now even more naturally, we can say, well, look, that plus or minus e to the 4c is in essence a constant in and of itself. How about we just call that our c2? By the way, you could just call it a c just as well. Sometimes kids are just looking at this going, yeah, what's so crazy about this problem? I don't see anything that seems to be an issue. Well, you know what? How about we do a little cross multiplying over here? I'd get y minus 2 is equal to, well, I'd have to distribute. I'd get c2 e to the 4x times y plus 2 c2 e to the 4x. That's just doing a little cross multiplying, right? And then how about we bring over the term with a y to the left. Simultaneously, we add a 2. And how about we also factor out a 2? Might wonder why I didn't even go back to calling it a brand new constant. We certainly could do that. How about over here, I factor out a y. And nice and simply, we come up with this explicit solution. Look at that. Looks wonderful, doesn't it? How about that? Well, I said you might lose something. Sometimes kids are like, I beg your pardon? What do you mean we might lose a solution? You're saying that what you've just written might not be representing every possible solution? Oh, indeed, that's the case. Let's go back to when we were dealing with differential equations that only had a y in them. Do you remember what we called those? You guys remember? Autonomous. You are absolutely correct. And then we said, wow, you know what, this would factor. And we talked about making phase portraits, didn't we? I'm not asking you to make a phase portrait, but can you envision two constant solutions coming from this autonomous differential equation? What would they be? Y equals 2. Y equals negative 2. Kids are like, yeah, so? I mean, obviously, you plug those in, it's going to work. What am I getting at? Y equals 2 and y equals negative 2 are solutions. You could find the y equals 2 if you choose clever. See, look at this box here. If you let your constant be 0, wouldn't you get y equals 2? But please hear this, no matter what you choose for your constant, try as you may, you'll never be arriving at y equals negative 2. So what are we learning here? What you're going to have to see, at least with these autonomous differential equations, ask yourself, hey, are there some constant solutions? Because we tend to lose them. In general, yeah, what we found is the solution. So that's all we've got for today. Of course, what you need to put, you'd say and y equals negative 2 in there. Wow, perfect timing for the end. Look at that. Good luck to you guys.